Welcome to Engineering Mechanics, Chapter 5, Distributed Forces, Centroids, and Centers of Gravity. Okay, little introduction. We're going to introduce some new concepts today. We're going to introduce the concept of the center of gravity. So everyone understands that the Earth exerts a gravitational force on every particle, right? Every particle on some object. Well, it turns out that you can replace all the individual forces on each particle with a single force of the same total weight applied at the center of gravity of the body. So that's the center of gravity. First moment of an area. The centroid of an area is analogous to the center of gravity of a body. Okay, and it turns out for a homogeneous body, they're actually the same place. The concepts of the first moment of an area is something that we're going to use to locate the centroid. We're going to introduce the theorems of Pappus-Gildinis, which makes it possible to determine the area of the surface of a surface of revolution or the volume of a body of revolution. And then we're going to talk about distributed loads on beams. At times we model loads across a beam as a distributed load, or what that means is it's going to be like a load per unit length. We will discuss how to determine the equivalent single load for this given distributed load and where to put it. Okay, let's talk about the center of gravity on a 2D body. Okay, the center of gravity of a plate. Consider a thin plate, okay, a thin homogeneous plate. So here's your potato plate, your potato chip. It's all the same thickness throughout, it's the same material throughout. Okay, there is a point that may or may not be on the plate where you can concentrate the weight of the entire plate and have the same moment about the origin. This point is what we call the center of gravity of this plate. It's true for a wire as well. That on this wire there is a point where you can apply the entire weight of the wire and have the same moment. And so how do you do that? Well, let's look at some of the moments about why. So let's look over here at this thing, right? So this force, the weight is going to cause a certain amount of moment about this axis, about the y-axis, right? So what we're saying is that the x bar, so x bar is how we will refer to the center of gravity. So the x bar of the whole thing times the entire weight, right? So you put the entire weight at one magic spot, x bar, away from the y-axis, right? And that's going to give a certain moment. We're going to say that is the same amount of moment as if you were to take a little chunk here times it so this little chunk's weight times its x, and then another little chunk here times its x, and another little chunk here times its x, and so on. That's what this x, delta w. Or you take that to the extreme, you make those little chunks infinitely small, and it's the integral of x dw. And the same thing is true for x. And so we're saying that there is that magic place, that x bar and y bar, where if you put the entire load, it has the same moment as if you treated every individual particle and each particle's own x or y distance. Okay, centroids and first moments of an area and a line. Okay, let's look at these let's look at an area. Okay, so consider our plate that we just had, right? So it had x bar weight is integral of x dw. Okay, if this is a thin plate, homogeneous plate, then the weight can be calculated by the area times its thickness, right? That gives it a volume, and the volume times the specific weight, and the specific weight is the weight per unit volume, right? And so we're saying x bar times this is the weight is equal to integral of x dw. Well, the differential weight at any little dw, any little point here, the differential weight is the differential area times its thickness times its specific weight. Well, you'll notice this gamma and t are constant on both sides. You can divide throughout, and you have x bar a is integral of x dA. This is what we are defining as the first moment with respect to y, and we're going to call it qy. So qy is the integral of x dA. That is the first moment with respect to y, and it's analogous with the first moment with respect to x is qx. Now you can do the same exercise, if you will, for a line. The weight of a wire, right? We have back to our little wire. What is the weight? Well, it's your length times your cross-sectional area. That's your volume times your specific weight, right? So this is your weight. And your differential weight is, at any point in time, your differential length times the area times the specific weight. And again, you'll notice the gamma and the a are going to cancel out. And so your x bar L is integral of x dl, and y bar L is integral of y dl. So these are the first moment with respect to x and y. Okay, so why do we care? Well, let's talk about some concepts, so some properties of these things. So when we talk about an area, an area that's symmetric. What that means is an area is symmetric with respect to some arbitrary axis if for anywhere where there's a point that's the equal distance perpendicular line on the other side that's the same. So for instance, everyone looks at this one. Hopefully it's obvious, about the x-axis, this is definitely not symmetric. About this axis, it's definitely not symmetric. But clearly you can draw a line here, and at any point anywhere along this line, you can go equal and opposite distances perpendicular to that line and get to this an equivalent point on both sides. So that means it's symmetric here. This one is a nice obvious one. This area is clearly symmetric about this axis right here. Well, why do we care? Because the first moment of an area with respect to a line of symmetry is 0, right? So this first moment of this area with respect to this line, b prime, or with respect to the y-axis in this case, is 0. The nice thing about that is if an area possesses a line of symmetry, its centroid lies on that axis. And if an area possesses two lines of symmetry, its centroid lies at their intersection. And not just two, but two or more lines, its centroid lies at their intersection. So look at this shape right here, right? So it possesses a line of symmetry right here. Well, it's the centroid of this thing, of this shape, lies somewhere on this axis. You don't know exactly where, but you know it's on this axis. Once you have multiple lines of symmetry, here's a centroid. This is one axis of symmetry. This is another axis of symmetry. For what it's worth, here's another one going to come through here, right? And the centroid is going to lie at their intersection. Now, sometimes an area is symmetric with respect to a point and not an axis, right? And so we're going to say an area is symmetric with respect to some arbitrary point O if for every differential element at xy, there's an equivalent of minus x minus y. So here, this is not with respect to an axis, but it's with respect to a point. So why do we care about that? Well, because the centroid of an area coincides with the center of symmetry, which is a nice aspect to that. If you have this, you know the centroid is going to lie at that center. Okay, so centroids of some common shapes. In the book, you're going to have two tables, this table and this table. Okay, so these are centroids of common shapes of areas. So here's a triangle. Well, hey, for this triangle, you can figure out the centroid. You know the y bar is h over 3. You can go through, and we'll a little bit later in this chapter, we'll do through direct integration, we'll calculate that. But you can go through and figure these things out. So this is our kind of go-to place. So there's these common shapes. So instead of having to reinvent the wheel every time, we can come to this table to get the information for these common shapes. They give you your x bar and your y bar. Please pay attention to where your axes are so that it makes sense. Those are for areas. These are for lines. So for this arc, or for this full arc, the centroid of this whole arc, the x bar, is going to be 0, right? Because that's hopefully fairly obvious. But the y bar is going to be right there, which turns out to be 2r over 3 pi, or the arc of a circle. You can figure it all out. One thing to be aware of: please don't use the line data for areas or the area data for lines. They're not interchangeable. You'll notice looking here, right? This one is 2r over 3 pi. If you came to this point, this area, you're going to find it's 4r over 3 pi, which is definitely not the same number. So please be careful of that. Okay, composite plates and areas. Well, for composite plates and areas, just as we considered, when we talked about the center of mass, or the centroid for these different things, we considered individual particles, right? Well, it turns out for a composite plate, you can do the same thing, but just instead of individual particles, you can talk about each individual piece of the composite plate. So we have our thing here, right? Our thin plate. Well, there is one spot where you can add up all the weight and apply it here at this magic location, x bar, y bar, and that has the same moment as if you took, say, this portion of it and you applied it there at its centroid, and this portion of it, this rectangular portion, and applied it at its centroid, and this triangular portion, and applied it at its centroid. And so what that says is that x bar times the sum of the weight, so the spot times the sum of all the weight, is the same as the sum of each individual's moments. X bar times the weights. So this is how you can go through and you can figure out what the centroid is of a composite plate. Hey, maybe we have a plate that's made up of a bunch of things that are of the shape that we just talked about right here. We have shapes that are known. So it's maybe made up of a semicircle and a triangle. Well, we can come over here and get this information, and then we can use that to determine the centroid of that composite plate. And for an area, it's the same thing. Remember, weight for a thin homogeneous plate, weight and area are pretty much interchangeable because weight is just your area times your thickness times your specific weight, and that's going to be on both sides, so those cancel out. So the composite area, your x bar times the sum of the area, is equal to the sum of your x bar times the area. Let's do example 5.1.